So, welcome back friends. So, we have been discussing about doing simple process in QED using the Green's functions methods. Now, these are Green's functions methods are equivalent to the Feynman diagram methods which you will learn in your quantum field theory and everything essentially. Okay. But they are much more powerful essentially, because you can see that these methods are very powerful. You can write the Feynman diagrams and everything. Even when the photon field, I assumed say for the process like Compton scattering. So, for example, for Compton scattering and other things, okay, for Compton scattering, where is the Compton scattering? Yes, for Compton scattering, where the photon is a dynamical field essentially. So, a photon comes not as a potential, a wave function is not a potential, but it appears as a dynamical field. It really comes, hits the particle and everything, especially in the relativistic regime essentially. So, the Compton scattering, so here and then there are other things like pair production and pair annihilation. In both this process too, we can treat the photon field as a photon wave function as a dynamical field, as a dynamical particle. So, we need to, so borrowing from quantum field theory, what we are doing is essentially that we are trying to quantize the wave function of the photon essentially, so as to give it as a particle interpretation. Now, you may ask me that okay, what are you doing is like a hopscotch, you are starting with wave functions and everything, and then using Green's functions method to solve these wave functions, and while doing so you are now suddenly saying okay, photon is no longer a wave function, but it is a the electromagnetic wave function. Instead, the radiation field is not a wave function, but it can be interpreted as a particle itself by interpreting it in terms of quantum harmonic oscillators like what we have seen here essentially. So, these are quantum harmonic oscillators. Okay. So, these are quantum harmonic oscillators. We did not do the full details actually. We interpret it in terms of simple harmonic oscillators, and then we saw that there is a, so we are giving some sort of hodgepodge thing essentially. You may think that this is like a hodgepodge, but it is not true actually. This method is much more powerful, and then what we said was that the Green's functions method is much more powerful. While it has some disadvantages, we will see the disadvantages and advantages of these methods essentially. Okay. So, this Green's functions method has some disadvantages in the sense that it does not automatically give you the particle interpretation very well. You have to take this wave function and then second quantize it and then okay, and second quantize it, and only then this wave function will be okay. Then the wave function can be interpreted in terms of particles. Now, this is true. And now, you may say that this is a very hodgepodge way, because you do not have, if you want to have particle interpretation, you need to do a quantization again essentially. But there are other things which are nice about this method. While this is a disadvantage, I completely agree with you, but there are other things which are very nice. And what we saw in the last lecture was that there was this case in which for the Coulomb scattering, we just took the wave function, the potential as just this potential, okay, as just a Coulomb potential. Essentially, we just took it as a Coulomb potential, okay, and this is like a static essentially. A bar is equal to 0 and a 0 is equal to ZE by 4 pi y essentially, and then we started using the Green's functions methods essentially. So, we started using the Green's functions methods, and what we found was that it turns out exactly like adding a propagator. It exactly turns out to be like adding a propagator, because that is not really surprising in some sense. Okay, because if you take this A0 and put it back into your Green's functions, and the Fourier mode of that is 1 by the Fourier mode of 1 by r is nothing but 1 by q square essentially. So, 1 by r is nothing but 1 by q square. So, if you want express everything in terms of the Fourier modes, and this just end up being this essentially. Okay. Oh, this is very difficult. Here this is the one. So, if you write the Fourier mode of this, essentially this just becomes 1 by q square essentially. So, okay, this is the thing which we have seen, and this is exactly like the propagator essentially. There is nothing difference in the propagator what we have seen for the photon, and that is the reason why I did not spend much time in deriving the propagator of the photon, and then you get this S matrix element in this particular fashion for the Coulomb scattering essentially. So, this is a simple example of the Coulomb scattering which you can use. Let us take one particular example of the Coulomb scattering, which is say neutron proton scattering essentially, say or electron proton scattering, which is a very interesting process, because this is exactly the same way of a Coulomb scattering essentially, and we will reverse it. We keep revisiting it again and again. Now, one more thing I wanted to mention, we also looked at the trace formulas in the computation of the amplitudes. So, I want all of you to look at all these theorems again essentially and solve them. Okay. So, good. So, the advantages of this method are that there are a couple of advantages, we will see both of them today. One of them is that even if you take static potentials, this thing works very well essentially, while you are taking the fields to be quantized essentially. In some sense they are Green's functions, you can use the propagator theory, you are not calling them, you are just dealing with wave functions all through. You define your X matrix element, the in state will be just multiplying this thing here. So, the in state is and the final state here essentially. So, the S matrix element I am computing it and exactly using this particular formula on the above, and then the and at the point of the interaction at y is the interaction point, when S the initial or the final state reaches y, it needs a propagator, and that is the point where all of them get interacted, and this A can be treated as an interaction which could be static essentially, it need not be just a dynamical field. Okay, this is the point. Now, you can use the Dirac wave functions and solve this. Now, this is the what I said was that here you can treat both A as a dynamical field as well as a static field essentially. So, in both the cases the method works essentially. Of course, if you take it as a dynamical field, it works for higher orders and it becomes the particle interpretation becomes clearer, the full quantum theory rigor will come. For there are other advantages. If you have some sort of a non-relativistic potential, say in that case also the Green's functions methods work very well essentially. That this is the entire point, that the Green's functions work very well for the non-relativistic potential also. So, that is the example we showed yesterday, and they give you very similar to the relativistic part essentially, and you can always go to the non-relativistic limit by taking beta is equal to 0 limit essentially. So, they give you the relativistic relation without the particle interpretation and everything essentially. Okay. Good. So, let us now apply this for electron proton scattering. question. Now electron proton scattering will be a pure Coulomb scattering, will be there is no annihilation, because though proton is positively charged, electron is negatively charged, it does not mean that they annihilate each other, because they are not of equal masses, they are completely different particles, because electron has lepton number, proton has baryon number, they have completely different quantum numbers. So they are completely different particles. Okay. So the only scattering they can have is a Coulomb scattering. Essentially the electron comes and goes, and then the proton comes and goes, and this will exchange a photon. So the time is in this direction, like we always put it essentially. So P1, P2, P3, P4. So this is the momentum direction. So this is the T channel P3, P4 minus P2 square essentially. So this is the energy. So this is the diagram, this is the T channel diagram. Essentially the proton is free, it is not bounded. Essentially the proton is free, not bounded. If there is a boundedness of the proton, then it has to have other potential also essentially. So if protons are bounded, we will see this example also in the later part essentially, then they will be non-relativistic. Okay, they will be non-relativistic. Okay. So now you can do the same example with the electrons replacing by with positrons actually. Okay. The and then you have okay you have various features of this, meaning electrons can be replaced with positrons with and you have the same results as we are now. Now the electromagnetic field is dynamic, and the electromagnetic field source, essentially the source of the electromagnetic field is the photon current. So psi bar proton gamma mu proton psi p is equal to j mu p. The proton current acts as the source for the electromagnetic field. And the equation of the motion for A mu would be box A mu is equal to J mu, and so you have the differential equation essentially A mu of x is equal to integral d mu 4 of y df x minus y j mu of y, and this df is a Green's function of the photon field essentially. This we already did actually in the previous lectures, because I introduced it, I already made it dynamical, but anyway I am just doing it for completeness. Okay, d mu is the force of the thing. So this del mu is del f x minus y is equal to del power 4 x minus y. Good. So this is your Green's function, and this Green's function I think I derived it del f, I showed it d power 4, but without the okay, 2 pi power square e power minus q x minus y df. In the momentum space this is just df by q square, where df of q square is equal to minus 1 by q square plus I epsilon. Okay. Forward in time is positive energy. Now how do I get this? Exactly the same way. Essentially you take the momentum, write the left hand side and right side, expand the left hand side and right hand side in terms of this Fourier modes. So you write this right hand side in terms of Fourier modes, and del square would be given by, in Fourier mode, 1 by q square, and the inverse of del square is nothing but 1 by q square. Okay. So the q square df is equal to the Fourier mode of del power 4, which is exactly this, and so df is equal to 1 by q square plus I epsilon. Okay. Now this we have already did it, but I am just doing it for completeness. Photon propagator. Now with this I can write down my the S matrix elements. Now we can write down the S matrix element or the scattering matrix element. So this is for the final state, this is the initial state times df x minus y j mu of y. Okay, j mu p, let me call it as j mu p because this is the potential generated by the photon field essentially. So j mu p, where j p mu of y psi bar p of gamma mu psi bar p of y. So S of phi minus I integral d power 4x d power 4y e psi f bar of x gamma mu psi of x df x minus y psi bar p of y gamma mu psi bar p of y. Now this will you can expand this each term, essentially j mu is equal to what, f is equal to what in terms of u bar and everything, and at the end of the day you end up this thing writing everything. This will be equivalent to some u bar pf sf gamma mu u of si pi e square by q square plus I epsilon u bar of p pf sf gamma mu ui pi si 2 pi power 4, and then there is a delta function factor. So the delta function factor, everything together, this is your Im essentially. This is very similar to what you do for with Feynman diagrams also. There is nothing different. This is your Feynman diagram calculation. Now you have done it just by Green's functions methods, and there is nothing else essentially. Okay. Whether you call it as Green's functions method or Feynman diagram calculation, this part is the same. Okay, this part is exactly the same essentially, except that if you think in terms of static potentials or non-relativistic cases or something like that, essentially the relativistic part is always the same. So, this turns out that if you write down the d sigma by d omega is equal to alpha square by 4 e square cos square theta by 2 q square by 2 m square sin square theta by 2 by sin power 4 theta by 2 1 plus 2 em sin square theta by 2 m by e is much smaller than 1. Okay, this m and that m are same essentially. So, I wrote capital M here essentially, yeah, m by. So, this is your electron proton scattering cross section. Okay, this is what you get essentially. This is the Coulomb cross section, and this gives you the nice little interaction essentially. Very good. Now the Green's function methods. Now you are okay. Now I showed you that it works exactly the same way if you have Coulomb interactions, right. Essentially you can take the Coulomb interaction to be static, or you can make the field dynamic and you get very similar results essentially. It is exactly the same results as long as the particles are relativistic essentially. The electromagnetic field itself need not be dynamic, or it can be dynamic also. It depends upon when it becomes dynamic is a question. When it becomes dynamic when it becomes when the higher order corrections become important, when the higher order corrections become important. Okay, as otherwise you can just treat it as non-dynamical static potential. But are there any other interactions, because we have focused so much on QED, essentially QED interactions, because we have focused so much on QED interactions. Are there any other interactions which are as interesting and where these methods are very powerful essentially, where the Green's functions methods are very powerful? You may also ask why these are all old fashioned methods and everything. Now why these are why one should study these things essentially, why one should study these things, and why these are important nowadays essentially, why they should be studied, I should be at all studied essentially. What makes them interesting to study? What makes them interesting to study? Now there are still certain things which are say for example, there are a couple of things in which these methods are still used essentially. One of them is dark matter studies. In the recent time, there are dark matter studies. There are a lot of interactions in dark matter interactions are not known. Okay, whether they are static interactions, and some of the times the dark matter particles are non-relativistic. Say for example, they are relativistic in the early universe, but they are non-relativistic in the galaxy. Okay, and so there could be while in the relativistic regime they move very fast, and you have to use the relativistic techniques and everything to calculate their cross sections and stuff like that. But once you are in non-relativistic within the galaxy, you have to use other methods to calculate whether they form bond states, whether they form clusters, therefore whether they form, what are the interactions of the dark matter with other meaning what are the interactions of the dark matter with other particles, standard model particles, and so on. So this should be these things require this kind of techniques. There is also one more thing, is essentially that we have been treating this coupling constant as very tiny, because the electromagnetic coupling constant is E square by 4 pi, which is roughly equivalent to 1 by 137, which is a very small number. Okay. But are there any cases in this Green's functions methods works very well also. Yes, actually it does work. The Green's functions methods or this wave function and propagator methods, propagator theory, also well this in perturbative this S matrix element in slightly not exactly strongly coupled also work very well to a certain extent in regimes with strong coupling. In regimes with strong coupling, like for example the example okay, we can think of is Yukawa interactions essentially. Okay. Here I have what I have in mind is not really completely so if you think of QCD, QCD has two parts. Okay. In the case in which it is perturbative, okay, in a perturbative case like for example if you think of quarks and gluon interactions, okay, in the regime QCD in the regime quark and gluon interactions, is perturbative. Okay. Whereas in the lower regime, when it is bound, when the nucleons are bound, inside a nucleus, we have a different kind of force which is the Yukawa force essentially. This is which is it is glued together by the strongly interacting Yukawa force. Now the Yukawa force is what we write essentially is V of r is a static force, we write it like minus E minus mu r by r, where mu is a constant close to the mass of the pion, where mu is a constant close to the mass of the pion. Pion mass is 139 MeV, roughly you can take it to be 139. Now, so all the if you have neutron proton cross section, say all the cross sections are Yukawa interactions. So just like in electromagnetic field theory, essentially the proton scatters with with in the presence of a neutron, when the neutron acts as a source to generate the Yukawa potential. The proton acts as a source or the neutron acts as a source for the Yukawa interaction essentially. So this is exactly like Yukawa interaction. Now the point is that it should be something like an electromagnetic force, but with a range. Okay. On the numerator there is a term which fixes the range because it is an exponential falling of term essentially, it should be something like a range essentially. So what is that range? The range is roughly essentially the range of the force is about 1 Fermi. And how do you get this 1 Fermi? You can also estimate it by the Compton wavelength of the pion, okay, which is 1 by lambda is equal to 1 by m, okay, which is roughly the 1 Fermi essentially, which is roughly 1 Fermi. H cross, put H cross and C accordingly. Now the point is that this is an interaction, it is exactly like electromagnetic potential. Now this has a constant on the top, which I told you that it is equivalent to the Yukawa mass, the particle mass, which is of the pion, which is pion. Now can it be made dynamical? Essentially that means can it be made dynamical in such a way that this would lead to some it is a mediator with of a mass of mu, with a mass of mu. So how do you know that? This can be thought of in dynamical form. So if you want to get the dynamical form, so what you do is you write the V of r is equal to y e power minus mu r by r, take the momentum expression, momentum space, in momentum space or the Fourier mode, this Fourier mode has the form y by q square minus mu square. This the Fourier mode of this in momentum square, 1 by r becomes q square and this exponential term mu r will just become the mass term essentially mu square. This is equivalent to the Klein-Gordon propagator. So this is equivalent to the Klein-Gordon problem. So this is wonderful, right? Essentially we started off with the potential and then we wrote it down as essentially in terms of this Fourier modes, and now we have a mediator because this is nothing but equivalent to the Klein-Gordon propagator, which we had derived some time ago essentially. The Klein-Gordon propagator, I think for the pions we derived it already, p square minus m square minus. So this is exactly the propagator we have. So this is exactly the propagator we have, plus I epsilon with a constant y, essentially with a constant y. So the Yukawa theory, which explains neutron proton interactions in terms, can be expressed in terms of a mediator with a pion, being mediator. Say for example you can have neutron, okay. So this is the main point essentially. So now you can have neutron proton to neutron proton, okay. So you can have various kinds of diagrams essentially for this essentially. So you can have neutrons are fermions, protons, neutron, proton, it is a pi plus. So what you can have? So you can have, if you want to have okay, let me draw it this way, neutron, proton, neutron, proton. By exchanging a pi plus, a neutron can get exchanged to a pion, proton, and a proton can get exchanged to a neutron essentially. So now neutron does not have a charge, but I am still putting some direction essentially just to give you. So there is no charge essentially. So the neutron, so the if you just look at the charge lines, the charge lines would be something like this, the pion charge and proton charge lines are conserved essentially. So the neutron can get converted into a proton by exchanging of a pion. Then there can also have neutron neutron exchanging a pi 0 to a neutron neutron, say for example. So neutron neutron proton proton, okay, just take a neutron neutron. Pi 0, okay. So pi 0 neutron neutron can exchange to a pi 0 essentially. Similarly you can have pi minus essentially with antiprotons or antineutrons and so on, so essentially. So there are several other diagrams which you can do for neutron proton scattering essentially. The theories, now these theories are inherently non-perturbative essentially, these theories are inherently non-perturbative, but you can have an idea how to calculate these things essentially, you can have an idea how to calculate these things. Now in this case actually there are various subtle things essentially, there is a deuteron and everything essentially, there is also the chiral current which acts as a source for the Klein-Gordon field essentially. So because the pion is a pseudoscalar, so those, so what happens is the actual current of the pion is psi bar p gamma phi psi essentially. So the so you can have proton proton scattering with a pi 0, neutron neutron scattering to a pi 0. So let me just write down a few things because I do not want to go further details, but say for example the source term essentially would be something like del plus mu square phi of x is equal to minus g 0 or y 0 psi p I gamma phi psi p, because the psi p is a pseudoscalar current essentially. So this is not the scalar current, it is a pseudoscalar current which acts as the source for the pion propagator essentially. So the pion equation of motion. Now you can the pion current essentially, this pseudoscalar current of the protons acts as, similarly the pseudoscalar current of the neutrons acts as source for this. Good, okay. So this is so I will not go further, but the important point is the theories with fermions, two fermions and a scalar interactions. So this would require, if you go into the Lagrangian, so this would require something like this psi bar I gamma phi psi p pion all sitting at the same interaction vertex with a coupling constant y essentially, okay, with a coupling constant. Such theories are called, these theories are called Yukawa interactions in the dynamical sense, okay. So we all know Yukawa potential essentially, from Yukawa potential we come to Yukawa interactions. This is also two Dirac fields with a scalar. So the interactions of two Dirac theories with a scalar, and this Yukawa coupling is typically large. Remember that it is not very small number, this can be very large number, large number in the sense in terms of perturbation theory, this could be touching 1, it cannot be 1 but it is touching 1. So this is when you use these methods essentially you get only, you do not get very precise answers, you only get an estimates essentially, you only, when you use these Green's functions methods, because you are using perturbation theory, at the end of the day you only get some sort of good estimates, but there could be 20 to 30% errors compared to QED, whereas in QED you get excellent answers compared to the experiment. Essentially you get excellent answers compared to experiment. So this is all about Yukawa interactions. So I will not I will stop here today essentially, and in the next lecture I will talk about higher order corrections for this. Okay. In these methods what happens to the higher order corrections, we have not talked about it, but the entire essence of renormalization and everything is contained in this particular sense essentially. So, and I want to cover this in the next lecture, and okay, so I will stop here. Thank you very much.